Hello, this is a quick video lecture all about absolute dating of geologic materials. Absolute dating is also sometimes called numerical dating or sometimes radiometric or radioisotopic dating. This field in general, or the subdiscipline within geology, is known as geochronology. So geo for earth, chron for time, ology for study of. Incidentally, I am a geochronologist, and so this topic is near and dear to my heart. As we've been discussing in class, there are many ways that we can assign relative ages to geologic events in the rock record, and we can create relative chronologies of what happened first, second, third, fourth, using the different principles that we've discussed and using our understanding of unconformities and of fossil successions in the sedimentary rock record. Sometimes, however, we really need to pin those events with numerical or absolute ages. Otherwise, we don't know the rates at which some geologic processes are happening. So we can do this numerical or absolute dating using techniques that involve radioactive isotopes. Radioactive isotopes, as I'll explain in a moment, are inherently unstable and decay. That decay happens at a known or fixed rate. So since we know that the decay is happening at a known or fixed rate, if we can count the number of decays that have occurred in a specific mineral, then we can say something about how old that mineral is. And so in that way, radioactive isotopes act as little clocks that are kind of ticking away in various minerals in rocks. Radiometric dates give the time a mineral began to preserve all of the atoms of parent and daughter isotopes, which requires cooling below a closure temperature. So here's a new concept. So if you think about an igneous rock forming, it starts as a magma, of course, by definition, and so therefore it is really, really hot because it is rock in the molten state. You got to get it really hot to do that, or really, really wet if you want to invoke flux melting. But even if you have water, it still needs to be very hot. Anyway, as that magma starts to cool, you already know that fractional crystallization begins to occur, with the highest temperature minerals crystallizing first, followed by lower and lower temperature minerals according to Bowen's reaction series. It is not until a mineral crystallizes that it can lock in the parent and daughter isotopes that might make up part of the structural framework of the mineral. So when the mineral crystallizes and closes, it does so below some threshold temperature. So that's what we mean by a closure temperature. The mineral has to first pass below that temperature before its internal clock can start ticking. Likewise, if the mineral or the rock that contains it is ever reheated, you could reset that radiometric clock. Something to think about. Igneous and metamorphic rocks can be directly dated using these isotope techniques that I'm going to discuss. Sedimentary rocks cannot, because by their very nature, sedimentary rocks are just the recycled equivalents of the original rocks that contained those little ticking clocks. And the sedimentary system is not hot, so it can't reset those clocks. Okay, so if we're going to talk about radioisotopic dating or radiometric dating, perhaps we should have a very brief discussion of what isotopes are. Isotopes are simply atoms of some element, but they have different atomic weight because they have a variable number of neutrons. So, for example, potassium. We'll use potassium as an example here. Potassium is a radioactive element. It has an atomic number of 19. That means that every single atom of potassium has 19 protons in its nucleus. However, the number of neutrons in its nucleus can vary. So you can have potassium atoms that have different atomic weight. If the potassium atom has 19 protons and 19 neutrons, then the atomic weight of the potassium is 38. But if the potassium has 19 protons, which by definition it has to have, that's what makes it potassium, and say 20 neutrons, then its atomic weight is 39. So potassium can have different isotopes that have these different atomic weights depending on how many neutrons it has in its nucleus. The same is true for all of these other elements that are circled here. Most famously probably is uranium. But all of the ones that are circled here have isotopes that are radioactive. So what that means is that each of these circled elements has an isotope, or more than one isotopes, that are fundamentally unstable, such that the arrangement of protons and neutrons in its nucleus is an unstable configuration. And so therefore, over geologic time, it will radioactively decay into a new atom of a daughter product that is more stable. So let's look at some examples. So when I refer to parent isotopes, I am talking about those isotopes of potassium or uranium that have a configuration of protons and neutrons in their nuclei that are fundamentally unstable. Those are the parents. So these three here on the left, these are all considered unstable parent isotopes. And by nature, they are not satisfied with the arrangement of subatomic particles in their nuclei, and therefore randomly, but at a known rate, over geologic time, they will decay into their stable daughter products. And so the isotopes that are shown on the right-hand side over here are stable products. And I want you to notice that in all cases, the daughter isotopes are different elements. So actually, the number of protons that existed in the parent isotope has been changed so that you've turned into new elements of a totally different chemical on the periodic table. In some cases, the total atomic mass stays the same. So 87 rubidium turns into 87 strontium. So you've just exchanged a proton and a neutron. And in other cases, the total mass changes quite a lot between the parent isotope and the daughter isotope. But regardless, we're not going to discuss that at length in a Geology 101 level. Regardless, you have the Earth naturally makes elements that are fundamentally unstable, and those elements over time will randomly, but at a known rate, decay to form the daughter products. Okay, so these arrows represent that decay process. Once a 87 strontium atom or a lead 206 atom has been produced, it will stay that way forever. And when these elements, when the parent elements on the left make up part of a mineral lattice, when that decay occurs, the mineral is trapping both the parent and the daughter inside if you're below the closure temperature. So you can take that mineral and essentially count the number of parent isotopes and the number of daughter isotopes and figure out how much time has elapsed. But again, it depends on knowing that known rate of decay. That known rate of decay we express as something called a half-life. A half-life represents the amount of time required for half of the parent population to decay into daughter product. Some radioactive isotopes have faster half-lives than others. Uranium-238 has a very slow half-life. Other isotopes like potassium are a little bit faster. So let's look at how this half-life works. It's an exponential decay. So let's start. So parent isotope in this graph is shown as the green line. So let's say that we crystallize some mineral below its closure temperature, and that mineral happens to lock in 16 atoms of the parent isotope. After exactly one half-life, so number of half-lives are shown here on the horizontal axis. After the passage of one half-life, exactly half of the original parent isotopes will decay away. So notice that after one half-life, if we trace this up, we are now at 8 parent isotopes. After the passage of 2 half-lives, we've got to cut that 8 in half, and now we are at 4 parent isotopes. After the passage of 3 half-lives, we are now at 2 parent isotopes. After the passage of 4, we are now at 1. And of course, after the passage of 5, we would be at 1/2, etc. Conversely, we could look at the daughter product. Just as the parent is exponentially decaying out of our mineral, the daughter product is exponentially ingrowing in our mineral. So after the passage of one half-life, so the daughter product is shown here in this blue curve, after the passage of one half-life, the daughter product, which was 0, is now 8, because half of the parent has turned into daughter. You're not losing or gaining, you're simply exchanging parent for daughter. After the passage of 2 half-lives, the parent's gone down to 4, but look, the daughter's gone up to 12. After 3 half-lives, 14, and notice that the daughter is asymptotically approaching 16 here at the top, and the parent is asymptotically approaching 0. But if you guys can imagine this, you can infinitely cut a number in half and never reach 0. But you're going to approach it. You're going to get pretty darn close. Another way to think about this that might help you to kind of visualize this process is by using boxes or these little gumball diagrams that exist. So let's imagine that our mineral, this time we're not looking at it in terms of a graph, but let's think about our mineral as having 16 atoms of the parent material. We would color them all green in this first box here. So at this early time after the mineral has crystallized, all of the isotopic or radioisotopic system that's in that mineral is parent. But after you let one half-life go by, so this represents the passage of one half-life, I'm going to abbreviate that T 1/2, notice that exactly half of the parent has decayed away. So now you're down to having only 8 parent. But what happened to the rest of it? Well, it turned into daughter. So now you've got 8 green and 8 blue. After the passage of another half-life, so now we're on to 2 half-lives, you're down to 4 parent and 12 daughter, etc. Oh, and let me just go back and say, in a cluster of isotopes, there's no way to predict which parent will decay next. That's why I'm saying that it is somewhat random. Okay, so we don't really know, which atom is going to decay to its daughter product and exactly when that's going to happen. We just know that averaged over time, a certain number will decay away, and we can quantify that by studying these isotopes and by saying, okay, well, we know that over this period of geologic time, you're going to lose half of your parent isotopes. We don't know exactly which isotopes or when that decay process is going to happen to each individual isotope, but we do know that over this period of thousands or millions or billions of years, half of the parent will be gone, will decay and turn into daughter. Now that we know that half-life, because scientists have been studying the half-lives of these radioactive isotopes for a long time, we can then go and take these minerals that contain both parent and daughter isotopes, and we can measure the ratio of parent to daughter using fancy mass spectrometers, and that's what's shown in this picture. Incidentally, I manage a lab that has 2 of these fancy mass spectrometers up on the 4th floor of Chaparral Hall, so someday if we're all back at CSUN together, I invite you to come have a tour of that lab. Here's another picture of yet another mass spectrometer. This is one that I used when I was a graduate student to do cool things like blow holes using a laser into minerals and leave these pits behind like you're seeing here. One thing that's really cool about radioactive dating is that you can go and put a numerical timestamp on igneous and metamorphic rocks. So in this picture, we have a granite at the bottom, which someone has used radioactive isotopes to date, and it yielded an age of 125 million years old. We know that this basalt, because it's also an igneous rock, is 80 million years old. And in this case, we've also dated this volcanic ash flow to 50 million years old. So we know something about the igneous rocks in this case. We can put absolute ages on those. What we can't do, however, is date the sedimentary rocks because, again, they don't have any primary minerals that just closed below their closure temperatures. They contain recycled minerals. But we can use cross-cutting relationships to figure out their relative ages. So, for example, we might not know the age of this Cretaceous sandstone here that contains the dinosaur bones, but we know that it must be younger than the granite. So we know that it must be younger than 125 million years ago, and we know that it must be older than the basalt because the basalt cross-cuts it. So we can't tell you exactly how old it is, but we can say that this Cretaceous sandstone has to be less than 125 and greater than 80. So I'll just abbreviate that sandstone. So using radiometric dating of igneous rocks, we can actually put brackets on the ages of sedimentary rocks. Okay, that's it. Be sure to go do your homework, your problem set number 3.